Year 11, welcome to week 6 of term 2, and our online learning continues. We're starting a new topic or a new chapter. We're in number and algebra still, the huge area of number and algebra, but we're moving into complex numbers. Actually, our chapter title is expanding the number system, complex numbers. In fact, what we're doing is we're just recognizing complex numbers because, well, believe it or not, we've been working with complex numbers, but just a part of complex numbers. Complex numbers, real numbers sit under the umbrella of complex numbers. But complex numbers have two parts, an imaginary part and a real part. We've only had our eyes open to the real part. We're going to open our eyes to the imaginary part pretty soon, but not this week. We're going to set the scene a little bit this week, and we're going to start with quadratics. Now, old hat really, isn't it? Quadratics. We've been doing a lot of quadratics in our lives, but what we're going to make sure we absolutely understand and are really fluent at is solving quadratics in different ways, but also solving quadratic inequalities, which would have been perhaps new back in October, November last year, but we've done a little bit over the course of the first few months of this course. So I'm thinking this week will be familiar for you, and it might be just a little bit after a torrid week or two. It might be just a little bit of light relief. So first we're going to look at quadratics, and we're going to look at solving. Now, when we solve quadratics, we well, there's a few ways we can do it, and we're going to look at each of these in turn. We can solve by factorisation, and that's our preferred choice, factorisation. That's when our solutions are going to be rational solutions. Although we sometimes find it very useful to solve by completing the square. Completing the square. If you haven't already cottoned on to the idea of speeding these videos up, then you should definitely experiment with that. And solving by using the formula, by the quad formula. Now, the quad formula is just a formulaic version of completing the square. It's completing the square when you start with ax plus by plus c equals 0, and you go through a completing the square process. You end up with the quad formula. So solving, so I should have said solving equations by factorization, by completing the square, by quad formula, and solving inequalities, inequalities. And I'll just tag that on the end here, solving quadratic inequalities. Quadratic inequality. So this is going to take us to the end of the week, although we will also meet something called the discriminant, which comes up in the quad formula, completing the square. We focus in on an area of the quadratic formula called the discriminant, gives us some information. So what we're going to do here is, perhaps in the past, quadratics has been a big section in itself. This is just laying a bit of groundwork for our first little foray into the complex number system. So, okay, let's kick off a couple of examples. What I want you to make sure really in this section is that you are very clear on what your methods are for solving different types of quadratics, and it's almost like times tables. It just reels off. You can't not know it. It's just instinctive, and you're away. So that's what I really want you to focus on. I know you can solve these things. I really want you to concentrate on becoming really, really fluent, really, really, really good at this stuff. So let me pop a couple of examples up. Okay, a couple of classic quadratics here. One of them, what we'd call a monic quadrilateral, or a monic polynomial, where my leading coefficient is 1, and part B, it's non-monic. So when it's monic, really we're just looking for two numbers that will do this for me. We'll multiply to -40 and we'll add to 3. So I come up with those numbers quite quickly. Be 8 and -5. my two numbers. So they, because it's monic, I just pop them straight in with x. So it's x plus 8, x minus 5. Now we're solving, I've just done that without even explaining what I'm doing, but I'm factorizing in this way so that I can use the null factor law. And that is that I know that if I've got a factorized form of an expression equals 0, then my factors each contribute to a solution by making them equal to 0. So therefore, we always take shortcuts with this, but this is what we mean. X plus 8 equals 0, or, not and, but or x minus 5 equals 0, because x can only be one thing at a time. So x is equal to negative 8, or x is equal to 5, and they're my two solutions to this quadratic, negative 8 or 5. Now we go over to part B, that's a 2x squared minus 7x minus 4 equals 0. So I go, and I'm still looking for two numbers, this time that don't multiply to negative 4, but negative 4 times 2, negative 8. And in fact, I haven't done anything different. If we just put a little 1 in front here for my monic, I'm still looking for two numbers that multiply to negative 40 times 1, which is negative 40, right? So I'm still doing that, but it just doesn't change it. So obviously I'm just left with that negative 40. But when this is non-monic, it is altered. It's negative 4 times 2, negative 8. I'm looking for two numbers that add to negative 7. So those two numbers multiply to negative 8, add to negative 7. So it looks like we're on negative 8 and 1, aren't we? So we take those two numbers, and in this case, I'm going to split my middle term into negative 8x plus x. So that's how I use these two numbers, 2x squared plus 8x. So that's, minus 8x plus x, right? The combination of which give me my negative 7x. But importantly, it allows me to comfortably factorize in pairs so that I have my factors. So I take out my 2x here, and I get this. And if I've done this correctly, I should get a common term here, a common factor here of x minus 4. So then I'm collecting like terms. I've got 2x plus 1, lots of x minus 4. Then I bring in my null factor law. So 2x plus 1 must equal 0, or x minus 4 is equal to 0, and therefore x is equal to negative 1/2, or x is equal to 4. And they're my two solutions to this quadratic. And I'm now going to ask you to complete exercise 3A from the textbook. It's a short exercise, but it's one worth doing, one where you'll just practice some of your factorizing. Remember, getting super expert at it. Okay, so you finished exercise 3A now, and we're going to move on to completing the square. Really important that we understand how to complete the square. It's not that straightforward. I know we'll pretend that it is because we're higher level students and it shouldn't really bother us, but it's okay if it does, because it's not perfectly straightforward. Let's have a look at a couple of examples. Here we're really just after the first step and key step, and that is when we complete the square, we have to make a perfect square out of something. So we've got to create a situation where often those first two terms are set in, aren't they? The x squared and the x term. We can't maneuver those much, but we can certainly, with our constant, we can change that, because we can balance that back out. We can add 6 and subtract 6. You know what I'm saying? So this is we're looking at a couple of examples here where we're just going to make this value of k such that we've got a perfect square. So I've got x squared plus 8x plus something. What's that something got to be? Okay, so in the first example, well, I suppose to backtrack, if I've got a perfect square, x minus 2 is probably not a great example. Let's say x minus 5, and I square it, then what we get is x squared minus 10x plus 25. And if I've got x plus 6 squared, then I've got x squared plus 12x plus 36. And what we like to point out at this point is that there is a relationship here between this this value here and this one here. And so my value of b and my value of c, my x coefficient and my constant. And that relationship is, well, we halve this. We halve the coefficient of the x, and then we square it to get the number, the constant number. So halve the x coefficient, divide it by 2, and then square it, and we're going to get the constant. Now that's a feature of any perfect square. So that's what we're going to use in this example. We're going to halve our 8. So in a, we're going to take 8, we're going to divide it by 2, and we're going to square it, and that's going to give us our k. So therefore, k is equal to 16 in this first case. And that would result in x plus 4 all squared. So in b, so our k in this case has to equal, well, I've got to halve my x coefficient, and I've got to square it. So that's 49 over 4. My value of k is 49 over 4, and what would x squared minus 7x plus 49 over 4 be? Always going to be positive, isn't it? By the way, a was therefore x squared plus 8x plus 16 was x plus 4 squared. So I've got x minus 7 over 2 all squared. So what pairs with the x is whatever that half of the coefficient of x is. Now if we head over to c, that's looking a little bit wilder, isn't it? 9x squared. I might here consider taking my 9 out, and this is what we would normally do when we're completing the square, because we do like our coefficients to be 1 for x squared, or we'd like a monic quadrilateral. X squared, so what have I got here? I've got 3x becomes 1/3 x. Remember, I've taken the 9 out, so it has to expand, has to distribute, so that's my 3x. And I'm going to leave a space here because I'm going to put something in there, and I'm just going to leave my k out there. Okay, so what goes into my position here? Well, I need to make a perfect square. I've got to have half of my x coefficient, and I've got to square that. So that's going to be in there. I'll just go with a different color. Is going to be the square of 1/6. Right, so I'm going to have 9 by x plus 1/6 squared. Right, but what happened there is, actually I'll come to that step in a second. What happened here is that this is 1/36. Right, so I've got 9x squared plus 1/3 x plus 1/36. But now what I've done is I've added in 9/36, or a quarter. So I have to take out, so I've got my plus k on there here, but I have to now, because I've added 9/36, I have to subtract 1/4. Okay, so now in order for this to be a perfect square, I need my k to be equal to 1/4, so that this all came to 0. So therefore, k is equal to 1/4, and what we'd have, so we'd therefore have 9x squared, what is it, plus 3x plus 1/4 plus 3x plus 1/4, which is equal to 9 outside of x plus 1/6 squared. Okay, so now just a couple of completing the square examples, and if you want to pause the video at this point, that'd be great, and have a go at the questions, then come back. So in part A, we're going to solve x squared plus 5x minus 24 equals 0 by completing the square. Now, if we weren't told to do so, we would just factorize this. I can see I've got 8 and -3 as two numbers that multiply to negative 24 and add to 5, but I don't have that option. I have to complete the square. So I have to write this as, therefore, I need x squared plus 5x. Now what I need here is, I don't want the 24 there actually. I'm going to take the 24 across. I'm going to clear a space here for my half of my x coefficient squared. And I'm just going to put that on both sides. So on the left-hand side, I have my perfect square of x plus 5 over 2 all squared. And on the right-hand side, I have 24 plus 25 over 4. So I have x plus 5 over 2 is my perfect square on the left. Right-hand side, I'm going to write this all over 4. So this is 96 plus 25, which is 121 over 4. I take the square root of both sides. X plus 5 over 2 is plus or minus square root of 121 over 4. Now they're both square numbers, so that's 11 over 2. I knew that this was going to be a rational solution because I could have factorized it at the outset. So now I've got x equals, I've got negative 5 over 2 plus or minus 11 over 2. So I can get my two solutions here by x is equal to minus 5 plus 11, which is 6 over 2 or 3, or minus 5 minus 11 minus 16 over 2, or negative 8. 3 or negative 8. Now if we'd factorized it, we would have got x plus 8, x minus 3 equals 0, and gone straight there to x is negative 8, or x is equal to 3. So we got there in 2 steps, but we didn't have that choice. We had to complete the square. So part B is a 2x squared minus 7x plus 1 is equal to 0. I have to solve by completing the square again. I don't know if this one factorizes, multiplies to 2. It doesn't look like it does. So it doesn't matter anyway. I've got to complete the square. And in order to complete the square, I need to take the 2 out. So I'll take the 2 out, and I end up with x squared minus 7 over 2x plus 1 over 2 equals 0. Now I didn't need to factorize that out because it's an equation. I could have just divided through by 2. That would have been a lot quicker. So I'll do that now. I'll just get x squared minus 7 over 2x, and I'm going to clear that half out the way. So it's going to be negative a half over the right hand side. I've cleared a space here to construct or to complete my square. I know it's going to be half of my x coefficient squared, so I just double the denominator. 7 over 2 becomes 7 over 4. You square it. I need to add it to this side as well. 7 over 4 squared. So therefore, I've got a perfect square on the left. It's x minus 7 over 4 all squared. And on the right hand side, I have negative 1/2 plus 49 over 16. So x minus 7 over 4 all squared. Just tidying up my right hand side, it's I'm to negative 8 plus 49. So what's that? 41 over 16. And then when we take the square root of both sides, we end up with plus or minus the square root of 41 over 4, square root of 16 being 4. Now I bring my 7 over 4 across, so I end up with 7 plus or minus the square root of 41 over 4. Okay, so now you get some practice with completing the square in exercise 3B.